Hello and welcome friends. Today we are diving deep into design of experiments or DOE. This is a powerful systematic method used to understand how multiple factors, that is inputs or X, affect our final result or our Y. Our goal is to find the perfect recipe for efficiency, that means least cost solution, and quality, that means best in class for customers. We are going to break down the process into 6 critical steps. Step 1 is clean up the process of spatial causes. Before we can study the underlying relationships, we must ensure our process is stable. We do this by eliminating spatial causes of variation, the unpredictable spikes or drops caused by things like equipment malfunctions or untrained operators. We use tools like failure mode effects analysis or FMEA to proactively identify what could go wrong and correct it, and put a control chart to put guardrails in place so that the special cause do not enter easily. If our process isn't stable, our experimental results will be noise, not signal. Stability is the foundation and necessary condition of DOE. Step 2 is understand factors of significance. Now that the process is stable, which we ensured in step number 1, we need to focus our attention on which potential inputs or access actually matter. We use hypothesis testing on historical or primary data to determine if factors of variation truly has a significance impact on our Y. For example, does temperature really affect the strength of our product, or is it a non-factor? Is decided using appropriate hypothesis test and concluding based on p-value, which is called as actual risk, and alpha, that is allowed risk. This step helps us narrow down our list from 8 to 15 potential variables to just 2 to 5 that are most important. We focus our experiment where the impact is greatest and hence on these 2 to 5 factors. Step number 3, select, set up and run experiments. This is where DOE officially begins. We select the appropriate experimental design, maybe a simple full factorial or more efficient fractional factorial design, depending on the number of factors. The design dictates the specific combinations of our axes we need to actually test. Next is we set up the equipment to allow for precise control of these factors, and then we carefully run experiments, collecting high quality data at every single test condition. Please remember, every data point here is precious and therefore we should collect data with great care. Step 4 is to analyze experiments to identify relationship y is equal to function of x. With the data collected, we move to analysis. We use statistical software to run ANOVA, which is analysis of variance. This tells us which factors are significant and crucially how they interact with each other. The ultimate output is predictive mathematical model, often a regression equation, which we can say y is equal to function of x1, x2, x3 and several others. This equation is the key. It quantifies the relationship, telling us exactly how much y will change for a given change in x. Step 5 is optimize for the best setting of x. Now we use our model which we identified in step number 4, which is y is equal to fx, to find the sweet spot, that is best optimal point. Based on our objective, whether it is maximizing the yield or minimizing the defect or reducing the cost, we manipulate our x variables in the equation to find the ideal settings. This often involves using something called response optimizer tool. It might tell us that the optimal setting is high temperature and a low pressure, and a combination we might never have guessed without DOE. And it will give us specific values of X around which it will give us the best result. This gives us an ideal operating conditions. Step 6 is validate best setting on floor. The math looks great till step number 5, but does it really work in the real world? The final essential step is validation. We implement the optimized setting on actual production floor and run the process for a defined period. We then use capability studies like calculating CP, PP, CPK, PPK to confirm that the new settings consistently meet customer requirements, showing that our Y is just not better but predictably and reliably better. Only after successful validation is the new process officially adopted.